Introduction to limits. The notion of limit is a fundamental concept of calculus and has been around for thousands of years. However, the formal definition of a limit, as we know and understand it today, did not appear until the end of the 19th century. Therefore, we will begin to understand limits from an intuitive point of view, just as our mathematical ancestors did. So, take a look at some examples. By the way, if you liked this video, don't forget to like and subscribe to this channel and activate the bell. It's very important for the continuity of this channel. We begin our exploration of limits by taking a look at the function f of x and its graph. Let's focus our attention on the behavior of the graph for values of x around x equals 2. To get an idea of the behavior of the graph of f near x is 2, we can use two sets of values, one set that approaches 2 from the left and one set that approaches 2 from the right, as shown in the table. As the values of x approach 2 from either side of 2, the values of y approach 5. Mathematically, we say that the limit of f of x as x approaches 2 is 5. Symbolically, we express this limit as follows. We use a horizontal arrow to represent the word approaches or tends to. But why so much hard work with the table? Why not replace x with 2 and get the answer 5? In fact, if all the functions were like this, we could simply substitute x for the given number to get the answer. Let's take a look at the next example. If we substitute x for 0, yields 0 over 0, which is meaningless. We represent this result with a hole in the graph when x is 0, and we say that the function is not defined when x is 0. Although x cannot equal 0, we can move it arbitrarily close to 0 to give a picture of how the function behaves in the vicinity of x is 0. In situations like this, the concept of limits is very important. To evaluate the limit of the function when x approaches 0, we begin by completing the following table to values around 0. In other words, x approaches 0 from the left and approaches 0 from the right. It's important to realize that the existence or non-existence of the function at x equals 0 has no bearing on the existence of the limit of the function as x approaches 0. In fact, it looks like we can make the y values as close to 2 as we like by making x sufficiently close to 0. Because this is true, we say that the limit of the function as x approaches 0 is 2, and we write this phrase using limit notation as follows. The limit of the function as x approaches 0 is 2. From this brief and informal description of a limit, we can think of an informal definition of limit. If f of x becomes arbitrarily close to a single number L as x approaches c from either side, the limit of f of x as x approaches c is L. This limit is written as follows. You have just seen how to find limits numerically and graphically. Fortunately, we do not have to go through these approaches each time we wish to find the limit of a function. There are many well-behaved functions, such as polynomial functions and rational functions with non-zero denominators. Such functions are known as continuous functions over their entire domains. In such cases, it's said that the limit can be evaluated by direct substitution. That is, the limit of f of x as x approaches c is equal to f of c. In short, the limit is simply the function value. Let's see how the direct substitution works. Evaluate each of the following limits. In order to evaluate the first limit, we substitute the value that x approaches into the function and evaluate the result. With 5 with x. Next, we perform the calculations. The limit as x approaches 5 is 14. In item B, we replace minus 2 with x. Next, we perform the calculations. The limit as x approaches minus 2 is 4. In item C, we replace 8 with x. Next, we perform the calculations. The limit as x approaches 8 is 2 times the square root of 2. In item D, we replace 2 for every x. Next, we perform the calculations. The limit as x approaches 2 is 22. In item E, we replace 4 with x. Next, we perform the calculations. The limit as x approaches 4 is 4. In this example, we need to find the limit of a constant function. Take a look at the graph. For any value of x, the function is 5. Therefore, the limit of a constant function is always equal to the constant value, regardless of the location of the limit point. In this example, the constant value is 5. We will see some properties of limits that will allow us to compute limits easier. Using these operations on limits, we can find the limits of more complex functions by finding the limits of their simpler component functions. The proof of some of these properties can be made using a formal definition of limit. This definition is known as the epsilon delta definition of limit. However, the epsilon delta definition is outside the scope of this video. We will see the epsilon delta definition of limit a few videos later, of course. Properties of limits. Let f of x and g of x be functions and the real number c is the limit point that belongs to their domain. Assume that L and M are real numbers and k is a constant, such that the limit of f of x as x approaches c is equal to L, and limit of g of x as x approaches c is equal to M. Then each of the following statements holds. The first property is known as scalar multiple. This property says that the limit of a constant times a function is equal to the product of the constant and the limit of the function. Evaluate the limits. We break up the limit into two separate limits. The limit of a constant is just the constant, and the limit of x squared as x approaches square root of 5 is 5. 3 times 5 is 15. The property 2 is known as sum or difference. This property states that the limit of the sum or difference of two functions is equal to the sum or difference of their limits. So to take the limit of a sum or difference, all we need to do is take the limit of the individual parts and then put them back together with the appropriate sign. This is also not limited to two functions. This fact will work no matter how many functions we have got separated by plus or minus. Let's see how it works. Pay attention. It's very simple. The property 3 is known as product property for limits. This property states that the limit of the product of two functions is the product of their limits. We take the limits of products in the same way that we can take the limit of sums or differences. Just take the limit of the pieces and then put them back together. Also, as with sums or differences, this fact is not limited to just two functions. Let's see how it works. Pay attention. It's very simple. The next property is known as quotient property for limits. This property states that the limit of quotient of two functions is the quotient of their limits, provided that the limit in the denominator function is not zero. As noted in the statement, we only need to worry about the limit in the denominator being zero when we do the limit of a quotient. If it were zero, we would end up with a division by zero, and we need to avoid that. Pay attention. The next property is known as power property for limits. This property states that the limit of the power of a function is the power of the limit of the function. We find the limit of the function as x approaches -2, and then we put the power back. 14 raised to the power of 3 is 2744. In this property, n can be any real number. In the case that n is an integer, this rule can be thought of as a special case of the property 3. The next property is known as root property for limits. This property states that the limit of the nth root of a function equals the nth root of the limit of the function. This is just a special case of the previous example. For root functions, we find the limit of the inside function first, and then apply the root. Pay attention in the example. Let's see one more example. This is a rational function, so we take care with the denominator. The domain of f is the set of all values of x for which the denominator is not zero. The denominator is not zero when x is equal to 6, because 6 is in the domain of the function. So we can calculate the limit by substituting 6 for x into the function.